Okay, so let's look at 3.8 linear quadratic systems. So last year you learned linear systems, and linear systems was solving two lines, and what that meant was solving where a line intersects with another line. So when you're finding the solution between a linear system, you're finding the point of intersection. Key concepts here is that a linear function and a quadratic function can intersect at 1 point, 2 points, or not intersect at all. So if I just show you what I mean by that, you may have something that occurs like this, where you have a parabola that may open downward like this, and you may have a line up here, and therefore this linear quadratic system has zero solutions because they never meet. You may have a situation that looks like this, where you have a parabola that opens up and a line that just barely touches this parabola, and it just touches once. So you have one solution. Okay? Or you may have another instance which is happens a lot more often, where you have a parabola that opens up and then you have a line that passes through the parabola twice. So these are the three instances that you may have. You may have no solutions, which looks like that. You may have one solution where it just touches once, or you may have two solutions where it crosses twice. Now, how do you find the points of intersection? So points of intersection of a line and a parabola can be found by graphing, which is the worst way, or by using the substitution method. That's what we're going to use. Okay, so let's take a look at example number 1. It says determine the point or points of intersection between f at x equals that and g at x equals that. As you can see, the f at x is a parabola and g at x is just a line, because that's just 6x minus 1. So we're trying to figure out when those 2 points intersect, or when those 2 points are the same. So figuring out when the 2 points are the same, basically you're figuring out when f at x is equivalent to g at x, when they are the same. That will be the point of intersection. So now on this side of the equation, I'm just going to plug in this stuff, and on this side of the equation I'll write that stuff there. So f at x is the same as negative 2x squared minus 5x plus 20, and that's equal to g at x, which is 6x minus 1. Now, to solve this, all I have to do is bring everything to one side, equals 0, just like a quadratic. I'm going to bring everything to the right side so that the x squareds are positive. So it would be 2x squared, and there's still plus 6 on this side. If I bring the negative 5x to this side, it's plus 5x. I have negative 1, and I'll bring the positive 20 to this side, will become negative 20. And on this side, I'm just left with nothing. So I end up with 0 equals 2x squared plus 11x minus 21. And now, how do you solve something that looks like this? You solve it by either using factoring or by using the quadratic formula if it's unfactorable. So I'll try to factor this thing using the crisscross method instead of decomposition. Two numbers that multiply to 2 are 1 and 2, and then the numbers that multiply to negative 21 are 7 and 3, or 1 and 21. So I'll try 7 and 3, negative 3, right? Because they have to multiply to 21, negative 21. So 2 times 7 is 14, and crisscross here, 1 times negative 3 is negative 3, and 14 minus 3 is 11, which is exactly what we were looking for. So now reading straight across, the first factor will be x plus 7, and the second factor, reading straight across, will be 2x minus 3. Of course, you can use decomposition to figure out these numbers here. And then this equals 0. That means if this bracket times this bracket is equal to 0, you have to solve for when this factor is 0 or this factor of 0. If the first factor is equal to 0, if x plus 7 is equal to 0, that just means x equals negative 7, and that is your first x answer. And then the second bracket, if 2x minus 3 is equal to 0, that just means 2x is equal to, bring this over, positive 3, divide both sides by 2, so x is equal to 3 halves, or 1.5 is fine. So those are not your two solutions, those are your two x values for your solutions, remember what we are looking for. We are looking for the points of intersection. And points are x, y. And if we have 2 points of intersection, that means we will have x, y, and another x, y. Well, right now, all that we found are the 2 answers for x. So we now have to use these 2 answers for x to figure out what their corresponding y values are, so that we have both points of intersection. See, the first point of intersection obviously is -7 something, and the second point of intersection is 1.5 something. So I'm going to use one of these 2 formulas to figure out what the corresponding values are. I will probably use the line because it's more simple. So I will figure out what g of -7 is. So plugging in g of -7, it's going to be equal to 6 times...
Semi-formal tickets are being sold in room 211 now. That's semi-formal tickets in room 211 now.
Apologize about the announcement, but that is 6 times -7 minus 1. So this is g at -7 is equal to 6 times -7 is -42 minus 1. That means g of -7 is -43. So therefore, the first point of intersection is going to be -7, -43. That's the first point of intersection. The second point of intersection happens when x is equal to 1.5. So I'll figure out g of 1.5 over here. So g of 1.5 is just going to be equal to 6 times 1.5. Again, I'm using the formula for the line. So g of 1.5 is equal to 6 times 1.5 is 9 minus 1. So g of 1.5 is equal to 8. So my second point of intersection is 1.58. So therefore, the points of intersection are, and the first point of intersection is -7, -43. And the second point of intersection is 1.58. So those are my 2 points of intersection for this problem. Okay, so let's move on to example 2. Example 2 is similar except a word problem. It says the revenue function for a production by a theater group is R at T equals all that, where T is the ticket price in dollars. I apologize for that announcement again. The cost function for the production is C at T equals that stuff. Determine the ticket price that will allow the production to break even. So we have revenue being this function here, and we have cost of the tickets being that function there. So T, remember, is ticket price in dollars, R is revenue, C is the cost. Now, the revenue is obviously a quadratic model or a parabola where the cost is linear. We are trying to figure out when the production will break even. So what does that mean, break even? Break even means that the production will not gain or lose money. So the profit will be nothing. Or, remember what revenue means. The revenue is all of the money coming into the cash register, all the money for the tickets, let's say, coming into the cash register. And cost is all the money going out of the register to pay for, the costs of the theater, such as running the theater or paying actors or paying employees or whatnot. So when you are breaking even, that is when the profit is 0. Or when the revenue is the exact same as the cost. So that's what we're trying to figure out. When is the revenue exactly the same as the cost? And so, again, from the last example, I'm just going to plug in revenue equals all this stuff, which is -50t squared plus 300t. And I'm going to plug in cost equals all that stuff, so that's 600 minus 50t. And now I'm going to solve for this. I'm going to figure out what the ticket price is so that the production breaks even when the revenue is equal to the cost. And continuing this, I'm going to bring everything over to the right so that the t squareds are positive. So this is going to be 50t squared minus 300t, if I bring the 300 to the other side, minus 50t, that's already here, and plus 600. And on this side, I'm just going to have 0. So if I continue this, I'm going to end up with 0 equals 50t squared. That minus that is minus 350t plus 600. And now I'm just trying to solve for this quadratic model here. Now, I just want to remind you up at the top here with our key concepts, it says sometimes one of the two solutions will be inadmissible. So just remember that if the ticket price ends up being a negative number as one of my answers, obviously that would be inadmissible because there's no such thing as negative ticket prices. There may be an option that you end up with two ticket prices that are positive though. So let's continue and let's solve this. So if I solve this, I'm going to try solving by factoring because that's what I always try. I can factor out actually a 50 from everything here. If I divide this thing by 50, I'm left with t squared. 350 divided by 50 is negative 7t, and 600 divided by 50 is positive 12. So then I have this simple trinomial here, and factoring that further, I'd use product sum integer rule. So if I use PSI, the product of that thing is 12. The sum of that thing is negative 7. So two integers that multiply to positive 12 add to negative 7 are negative 3 and negative 4. Let me double check. They multiply to positive 12 and add to negative 7. So this will be 50, and then I will have x